So we've got a little review to do today on for Exam 6, Chapter 15 on solutions. So I've taken the review document and I've marked off some ahead of time. I've highlighted them so I won't have to go back to my original copy and figure out which ones I want to do. And I've got a new mouse, and I don't think it might work okay on this one. I can move the cursor around, but it's not going to let me scroll too well unless I can snag that right there. Or maybe go down here at the bottom. That works better. There we go. Okay. So enough playing with my mouse. Let's look at some of these problems. The first few, let me turn that off. The first few are each one. Just do the whole first page. And then we'll start getting duplicates. I'll skip a few. All right. How many grams of calcium chloride are needed to prepare 5.17 liters of 0.5 molar calcium chloride? So what do we know? We know the compound is that. And we know it's going to be in some kind of solution. Actually, for molarity, it doesn't matter what the solution is made of, but most of them are going to be aqueous for our purposes. And then we're told that we need 5.17 liters. So the volume is going to be that. And the molarity is going to be this. 0.5. There we go. So I would go to the definition. What's molarity? Molarity is moles per unit volume, and volume is in liters. Then you look and see what you got available. We have volume, we have molarity. We got that one, we got that one. We can get this one out of that expression, but that's not the end of it, because that only tells us moles. And the question is, how many grams? Okay, so it's really a two-step problem. If we solve for moles, then we get molarity times volume. And we can do that really easily. Liters times 0.500. And you can put molarity there. But if you've got a complicated calculation, sometimes it's better to interpret the molarity. What does it mean? It means moles per liter. That way, you can cancel the liters and you know you're left with moles. It's just an insurance policy. So a half of 5.17 would be the number of moles. Would be 2.085. No. 2.5. I'm going to use my calculator. Sometimes I can do these in my head and sometimes I can't. Always on the right track. 585. So that's the number of moles. And you'll notice that we've only got 3 significant figures here and here, but I'm keeping 4. And the reason I do that is to avoid rounding error. We'll knock it down to 3 when we're finished. But now that we know moles, we can find how many grams, because molar mass is given. 111.0 grams per mole. So if we start with this many moles, 2.585 moles, then our conversion factor is moles on the bottom, grams on the top. Right? And that's 111.0 grams per mole. So now the moles cancel, and that leaves us with grams. So 286.94. Grams. And we're going to round it off to 3. So that should be 287 grams. Right there. Okay. All right, that's number 1. Got a light today. Got one online and one face to face. Number 2. What mass of solute is contained in 64.9 milliliters of 2 molar sodium bromide solution? So we know we have sodium bromide solution, and for simplicity, we're just call it aqueous. And we know that this is 2.00 molar, and we know we have a volume of 64.9 milliliters. That's everything we know. Now the question is, what's the mass? Okay, so here we have again a situation where we can use these to find out the moles, but then we need to convert that into mass. Yeah. So if we have our expression again, and then we're going to solve for moles, equals molarity times volume. Then in this case, we have to be sure that our volume is in liters. So we just move it 3 to the left. That gives us 0.0649 liters. That should be the number of moles. .298 times 10 to the minus 1. Okay. Now we got a number of moles. We just need to convert that to grams. Our conversion factor will cancel moles and leave us with grams. So again, when you see grams and moles as a quotient, automatically think molar mass. So what's the molar mass of sodium bromide? We'll go to our periodic table and see what sodium is. Rounded off to 2 decimals is 23, right? And then how about bromine?
Rounded off to 2 as well.
Hmm?
You want it rounded off to 2 as well?
Yeah, I usually do. 79?
Yep. So it'll be 79.9.
9.9. Okay, so 102.90, 102.90 grams per mole. Now we just multiply that times the number of moles. And I get, let's see, rounded off to 3 places. I can get 13.4. Oops. Grams. And let's see, there it is right there. Okay, moving right along. Let's see if I can do this. Here. 3. Okay. I found this problem, number 3, in 4 different places in the review document. And it's a complicated problem, so I'm going to save it. We'll come back to 3, and then we'll skip through. I've got indicators here for where to go next. So work on this one, find an answer, and then we go to number 6. Use the same scenario to find the answer to number 6, and then it sends us to 47, I think, and then that one sends us some down the line. So we're going to come back to 3 and get some of these simpler problems out of the way. Let's see here. All right. So we're going to go down to number 4. The molarity of chloride. We want to know the molarity of chloride ions. Molarity of chloride. In 110 milliliters, milliliters of a solution containing 3.22 grams of calcium chloride. Okay, the solution contains 3.22 grams of calcium chloride. We want to know the molarity. Okay. We want to know the chloride ion concentration in molarity. Okay. So I think what we should do is calculate the molarity of calcium chloride. And then in solution, it actually breaks up into calcium ions and 2 chloride ions. So then we can take the molarity of this and convert it to chloride ions from there. That make sense? Maybe not so much now. Okay. Let's say the question was, what's the molarity of calcium chloride? You could do that. Just convert this to moles. Grams, moles. So we need a molar mass for calcium chloride. Let's see, calcium is 40.08. And 2 chlorines, 3545 times 2. Add that in there. So that's 110.98. 110.98. Grams cancel, leaves us with moles. Divide that into 3.22. There we go. 2.901. 2.901 times 10 to the minus 2. Yeah, looks reasonable. So that's the number of moles of calcium chloride. Now we have, we can go 2 directions here and get to the same answer. If we're only interested in molarity of chloride, we could do, like I said earlier, we could convert this moles per 0.11 liter and find the molarity of this and then convert that to chloride. Or we could say, if we have this many moles of calcium chloride, how many moles of chloride do you have? You have 2 times that. You have that many moles of the unit, this whole unit, which means you've got that many moles of calcium, plus you have twice as many moles of chloride. We're talking about numbers of things. Right? If we have 1 mole of this, we have 1 mole of calcium and 2 moles of chlorine. Okay, so if we just double this, now we have moles of chloride. 5.803, 5.803 times 10 to the minus 2 moles of chloride ions in that same volume, 0.110 liters. And I get, excuse me, 3 significant figures. Rounded off, I've got 0.528. And let's see, is that up there? There it is. Okay. We could have gone the other route. It would work just as well. Okay, 5. What volume of 12 molar nitric acid is required to prepare 6.71 liters of 0.1 molar nitric acid? Okay, notice we have 2 molarities listed here, 12 and 0.1. So I think we're in a dilution situation, which means if we're talking molarity only, it just says molar first here, concentrated molar, dilute molar. We don't have to think about how many hydrogens each molecule produces. So if we say concentrated molarity equals 12 molar and dilute molarity equals 0.100 molar. And what else are we given? Volume. We want to prepare 6.71 liters. Oops. The dilute volume is 6.71 liters. The question is, what volume of the concentrated solution do we need to dilute to this volume? That's the question. I like to extract all the information from a word problem and put it on the board in a more recognizable form. And we know that molarity of concentrated times volume of concentrated equals molarity of dilute times volume. And if we solve for the unknown, that means this one equals dilute volume dilute divided by concentrate. And then you just plug in your numbers. So the molarity of the dilute is 0.100, and the volume of the dilute is 6.71 liters, and the molarity of the concentrate is 12. Okay. So now what units will the volume of the concentrated be in? It'll be in liters. Is that, and you look at your answers, yep, all of them are in liters. So we got the right units. So we just do the calculation. 12. I get 5.59 times 10 to the minus 2. Oh, none of them are in scientific notation. So let's convert this to standard. Move it toward 2 to the left. 1, 2. 0.0559 liters. Now it matches. Sometimes in multiple choice test, the answers, the possible answers give you clues as to where you're headed with your problem. Let's see, we're going to skip 6 also because it's, let me see if I can page it. There's 9, but it needs to scroll a little bit. There it is. Oh. No. There it is. I was trying to move the wrong one. Yeah, get 2 of them on there. Let's see, it's still showing. Yeah, showing. All right, number 9. You have 3 ammonium sulfate solutions on a lab table in front of you. All the solutions came from a 500 milliliter volumetric flask containing 3 molar ammonium sulfate. So each one of these is the same concentration. They're just different volumes. Okay? The question is focusing in on solution 2. Okay? So we only have to be concerned with this information right here. The rest of it is blue smoke. Blow it in your face to confusion. That's the purpose of multiple choice questions. Word problems especially. Okay. Ammonium sulfate. Okay. This is a 3- charge. This is a 1+ charge. So that's 3. This is a solution. What concentration? 3 molar. And we have 68.7 milliliters. 68.7 milliliters. Now, how many moles of ions does solution 2 contain? This is a unit conversion problem, really. You have 3 molar of this formula. And if we want to convert to how many moles, remember, moles equals molarity times volume. So we can say the number of moles equals molarity, 3.00 moles of compound per liter of solution. Okay. And then the volume is 0.0687 liters of solution. That'll give us moles of compound. But the question is, how many moles of ions are there? So I'm going to wrap around here. So if we find moles of compound, how many ions, how many moles of ions per mole of compound? That's your conversion factor. Moles of ions. Well, we have 1 here. We have 3 there. So there are 4 ions for every formula unit. The ratio is 4 to 1. Now, that's the thinking part. The rest is number crunching. Did I lose anybody? Okay. 0.0687 times 4 times. So I get 0.824. 0. 0.24 moles of ions. Let's see, is it here? No, I did something wrong. Oh. Did I do this right? 68.7 mils. 1, 2, 3, that's right. That's liters. This is molarity. Do that again. And then times 4. No, I got 824. Why is it saying 618? Is my formula? My formula's wrong. Got it. I looked at sulfate and thought phosphate. This is a 2 minus charge. This is a 1 plus charge. That means 2. So this has to be 3. Point 618. Okay. All right, number 10. 10 is the definition. Mixture of sand and water is what? Let's see. Mixture of sand and water. What's a mixture? Not a compound. It's not a solution. It's a heterogeneous mixture. So we look to see, is there a heterogeneous mixture here? Nope. None of these. None of these fit the bill. Well, huh. No, who? Yeah, it is. No, who? Supposed to be able to freeze the cursor and page. No. No. See it. All right. The chemist needs 225 milliliters of 3.1 molar hydrochloric acid. What volume of 12 molar must be dissolved in water to form this solution? That's another dilution problem. So we want to end up with a dilute solution. Actually, 3.1 molar is not dilute, but it's more dilute than 12 molar. So if you want to end up with a dilute volume of 225 milliliters from, and the dilute concentration is 3.1 molar from a concentrated solution of 12 molar, then we can calculate the how much of the concentrated solution is required to dilute to this volume. And the answer is in milliliters. So for dilution problems, you don't have to change the units of measure because they cancel in the operation. And if you keep these in milliliters, then your answer is going to come out in milliliters. So we need this one times this one. right? Equals the dilute. That. So we solve for the one we don't know, and that makes, and then we just plug in our numbers. So the concentrated is 12 molar. The, oh, that's not right. That's not right. That's not right. That's the mistake right there. Okay. So we know this one and we know that one. Start over again. This one's going to be concentrated. So the molarity of the dilute is 3.1 molar. The volume of the dilute is 225 milliliters divided by 12 molar. There we go. Okay. Round it off to two significant figures. That's our limit. 3.1 is only 2. So round it off, I get 58 milliliters. 58 milliliters. Now it's working. Number 13. Let's see. You have 250 milliliters of 4 molar sugar solution. You add 376.3 milliliters of water. Determine the concentration of sugar solution after the water has been added. Okay. This is a dilution problem, but you've got to be careful that you have the right amounts for each one. So we need concentrated molarity, concentrated volume, dilute molarity, and dilute volume. So we start off with, we're going to dilute it. So 250 milliliters is concentrated volume. From a concentrated solution of 4 molar. Right? The question is, what's the concentration of the dilute? Now, what's the volume of the dilute? It says we're going to add 376.3 milliliters, but you've already got 250 milliliters in there. So the dilute volume is 250 plus 376.3. That's the trick to this problem. You got that?
626.3.
Now we can solve the problem. So let's see. This one's going to be times this one divided by this one is equal to the molarity of the dilute. So the concentrated is 4 molar, and the volume of the concentrated is 250 divided by 626.3. There we go. Let's see, 4 times 250 is 1,000. 626.3. Okay, I get 1 point, how many? 3 significant figures. 1.60. Right. 1.60 molar. Right there. Okay. Agent still works. Wait a minute. Went the wrong direction. There it is, 14. You have 2. Okay, here's a logic problem. You have 2 hydrochloric acid solutions labeled A and B. Okay, so you got solution A, solution B, and they're both HCl. Okay. Solution A has greater concentration than solution B. So the molarity of A is greater than the molarity of B. Which of the following statements is true? Okay. A says, if you have equal volumes of both solutions, so volume of A equals volume of B, solution B must contain more moles of HCl. I don't think so. If the concentration is greater than equal volumes, then this one's going to be, this is actually going to be this way. That's the other way. So A is out. How about B? Adding more moles of HCl to both solutions will make them less concentrated.
Concentrated.
Right, because there's your definition. If you add more moles, you get a higher concentration. Okay, how about C? To obtain equal concentrations of both solutions, you must add a certain amount of water to solution B. If you add water, you're diluting it more, correct? C is false. D, at least 2 of the above statements are true. Wrong. And E, if you have equal moles of HCl in both solutions, solution B must have a greater volume. So you have equal moles. Moles of A equals moles of B. But the concentration in this one is less. So the volume of A must be greater than B. Oh, excuse me.
Backwards.
I got it backwards. It's the other way around. The denominator has to be bigger to make the concentration less. Right. So, easy answer. All right, 16. Let me see if I can. Oops. Wrong one. There it is. There we go. 16. 116.9 gram sample of nitric acid solution. 116.9 grams of nitric acid solution has 70% HNO3 by mass. So the concentration here is 70% by mass. That means the solutes in mass and the solvent And the solution is in mass also. Okay, what does that mean? That means 70 grams of HNO3 per 100 grams of solution. Okay, so it contains an answer. The answer informs our direction of our problem solution. The answer is in moles of HNO3. So all we can find from this is how many grams of HNO3 there are. Right? If you have this many grams of solution, then we can find out how many grams of HNO3 there are. Right? 116.9 grams of solution. $70 grams of HNO3 per 100 grams of solution. So that cancels out. 70 times that divided by 100 is really 0.7 times 116.9 is 81.83. Grams of hydrogen nitrate. Because it's not in solution anymore. We've taken it out of solution, and this is how many, that's the mass that we have. Then we convert that to moles. Grams, moles. We need a molar mass for HNO3. Well, I know hydrogen is 1.01. Nitrogen is 1401. 3 times 16 is 48. 63.02. Okay. Grams cancel, leaves us with moles. So divide that into 81. And I get how many? 4 significant figures. 1.298. Right? Looks like it rounded. They rounded it off to 1.30. Didn't have to do that. But that's the best answer. Okay, 17. Given on time. Determine the normality of a base if 93 milliliters of 1.8 molar HCl is required to neutralize 52 milliliters of it. Okay, in this case, we're talking about a titration, an acid-base reaction. And normally what you would say is molarity of the acid times the volume of the acid equals molarity of the base times the, I say velocity of volume. I'm mixing a little physics in here. Volume of the base. Now, we can use this expression if both the acid and the base are monoprotic. Well, the acid is monoprotic and the base is monohydroxyl. But it doesn't say that. So what we have to do is say the normality of the acid times the volume of the acid equals the normality of the base times the volume of the base. What's the normality of HCl? If HCl is 1.8 molar, it's also 1.8 normal because there's only one hydrogen per molecule. So the molarity and the normality are exactly the same. Okay. All right. So now we can say, what's the normality of the base? Well, this is our unknown. We know the normality of the acid, 1.8. The volume of the acid is 93 milliliters. And the volume of the base that's neutralized is 52 milliliters. Okay, so we have one unknown in this formula. That means the normality of the base is equal to, this one comes over here, so this one is 1.8 normal times 93 milliliters divided by, this one comes over here, the denominator, like that. Okay, did I lose anybody? I just solved this equation for the normality of the base, and then plugged in the numbers. So if we do the calculation, 1.8 times 93 divided by 52, I get, let's see, two significant figures. 3.2. The base is 3.2 normal. Okay. Now, the beauty of this is it doesn't matter what the base is. It's irrelevant to answer the question. The base could be sodium hydroxide, in which case that would be molarity also, because there's only one hydroxyl in sodium. It could be calcium hydroxide, in which case the molarity of the calcium hydroxide would be a half of that, 1.6 molarity, because each calcium produces 2 hydroxyls. Okay, that's 17. And 18. Magnesium metal reacts with hydrochloric acid to form magnesium chloride and hydrogen gas. Okay, magnesium metal reacts with hydrochloric acid to produce, let's start over again. Magnesium metal plus hydrochloric acid reacts to produce magnesium chloride, which is soluble, plus hydrogen gas. There we go. Let's see, are we going to need the balanced equation? Yes. Suppose we react excess magnesium metal with 19.8 milliliters of 3 molar hydrochloric acid. Collect all the hydrogen in the balloon. What's the expected volume of the balloon? Okay. So you're going to have a balanced equation. Let's see, 1 magnesium, 2 chlorines. That's it.
Yeah.
Okay, now what are we given? I'm going to put it up here on the board next to the equation. Excess magnesium. We'll never run out of that. Hydrochloric acid is 19.8 milliliters of 3 molar. Okay. Collect the hydrogen gas, so we're focused on this as a product at 25 degrees and 1 atmosphere pressure. Okay, that's everything we know. Question is, what's the volume in the balloon? It's filled with hydrogen gas under these conditions. All right. So if we need to know the volume of that balloon, what do we know about it? Have we done gas laws yet? Oh, forget this one. This,
I'm confused.
yeah, I'm sorry. This one is beyond you. You could find out how many moles of hydrogen are produced. You're capable of doing that, right? But to go from moles to volume, you need the information that we haven't covered yet, right? So don't panic. You won't see one like this on the exam because that wouldn't be fair. We could calculate the number of moles. Why don't we do that just as an exercise? It won't be one of these answers, but it will be an answer. So remember, when you go from this place to that place, you have to be in moles. So how many moles do you have here? Well, you have 3 molar. Then you need the volume, 0.0198 liters, to give you moles. Uh, 5.94 times 10 to the minus 2. 5.94 times 10 to the minus 2 moles of HCl. How many moles of hydrogen? Well, what's the ratio? It's 2 to 1. So for every 2 of these, you get 1 of those. We'll just do it longhand. The ratio then is 1 of these for every 2 of those. That means divide that by 2. 2.97 times 10 to the minus 2. Of hydrogen gas. So if he gave you that problem on an exam, I have to stop here because that's as far as we've gone so far. We haven't picked up gases yet. Once we do gases, you can take that information, this information, that information, and you can answer the question. But this is as far as we can go right now. We could convert that back to grams, find out how many grams of hydrogen. Right? That's doable. All right, that was 1822. Which of the following solutions contains the smallest number of ions? Okay, what I'm looking at is an assembly line, Henry Ford. So if we set it up like this, A, B, C, D, and E says at least 2 of the above contain the smallest number. That means they have to be equal. Okay, that's probably not the answer. So we have 246.8 milliliters, 46.8 milliliters of 1 molar sodium sulfate. Remember, volume times molarity equals moles. This is not in liters, right? But if you multiply molarity times milliliters, you get millimoles. How do I know that? Well, if we multiply 1 times that, how many do we get? We get 246.8, and I'm calling them millimoles. If we convert this to liters, we get 0.2468 liters times 1. That's 0.2468 moles. What's a millimole? A millimole is 1,000th of a mole. So 1,000th of the mole would be 1, 2, 3. There you go. We just changed the units. Did I lose you? Okay. So the reason I'm leaving it that way is it just kicks out a step. We don't have to convert it to liters. And we're really only looking for the numbers of ions. So as long as we're in a unit that represents numbers, that works. But this is millimoles of the compound. How many moles of ions does that represent? Well, if that's millimoles of compound, we need a ratio. I should have started over the other side a little bit. 246.8 That's millimoles of compound. Then the ratio is compound to ions. Okay. What's the ratio? You need to know the formula. Sodium sulfate. There are 3 ions for each formula unit. Okay. The next one, 539.8 milliliters times 1 molar. And then let's go ahead and do the conversion. What's that? Lithium nitrate. Lithium nitrate. Lithium is +1 because it's a alkaline metal. Nitrate is -1, so we've only got 2 here. 2 ions for 1 compound. Okay. Next one, 305.6 milliliters times 2 molar. And then what's the conversion here? Potassium hydroxide, KOH. Potassium is +1, hydroxide is -1. We only have 2. 2 ions, 1 compound. And then D is 189.6. And it's also 2 molar. And then we can convert that to ions. Iron 3 chloride. Iron 3 chloride. 3 plus, 1 minus, we need 3 of those. So that makes 4. Now we can do the calculations. 246.8 times 3 is 740. So this is 740 moles of ions. This is 539.8 times 1 times 2 is 1,080. The next one, 305.6. 305.6 times 2 times 2 again. That's 1222. And 189.6 times 2 times 4 is 1517. Okay, so here's the winner. Hey, no 2 of them are alike, so he's false. All right. 25. Assume that vinegar is a 0.852 molar solution. So we've got vinegar. Oh, and they give you the formula. That's nice. Acetic acid is the formula. So it says HC2H3O2 aqueous is 0.852 molar. What volume of 0.2136 molar sodium hydroxide? So we've also got sodium hydroxide aqueous. It's 0.2136 molar. Would be needed to neutralize 6.89 milliliters of vinegar. So the volume of the acid is equal to 6.89. Okay. This is a titration. you want to, first, let's look at the nature of the molecules. There's one hydrogen here, there's one hydroxyl there. So the molarity and the normality are the same values. Right? So we can use the M1V1 equals M2V2, or MAVA equals MBVB, acid base. The number of moles of this has to equal the number of moles of that. That's why we say MAVA equals MBVB. This equals to moles, right? Moles of acid, moles of base. If they're going to neutralize, these have to be equal. And what we're saying here is actually moles of hydrogen ions, moles of hydroxyls. That's why we can say molarity here instead of normality. But if you have, say you have acetic acid here, no, not acetic, citric acid. Citric acid would be 3 hydrogens. So you would have to calculate what is the normality and use NV instead. But since they're 1 to 1, we can use molarity. Works just as well. All right. So this is the formula we're going to use. Molarity of the acid, 0.852. Volume of the acid, 6.89 milliliters. And notice I don't have to change milliliters because this is a ratio where the milliliters will cancel. And the molarity of the base is 0.2136 times the volume of the base. That's our unknown. So we just solve for the unknown. That times that divided by this gives us the volume. I get 3 significant figures. 27.5. 27.5 milliliters. Right there. I could do it this way too. Right there. Get that out of the way. Okay, 26. For the reaction between 200 milliliters of 0.1 molar silver nitrate and 95 milliliters of 0.1 molar sodium chloride, the concentration of silver ions in solution after the reaction is complete. This one should have been, I should have dovetailed that one with 3 and 6. So let's come back to 26 because I'm going to do 3 and 6 and then 26 needs to be part of that also. How did I word that? Continued. Continued number 26 will be continued 47. And then this one needs to go to 26. We'll come back to that one. Then we only have to write the chemistry up on the board once. Okay. 29. Nitric acid solution containing 71% HNO3 by mass has a density of 1.42 grams per milliliter. How many moles of HNO3 are present in 2.36 liters of this solution? Okay, this looks to me like a unit conversion. you've got 71% HNO3, and you're looking for number of moles. Okay. 71.0, what does that percent mean? That means grams of HNO3 per grams of solution. Actually, our starting point is here. This is what we possess. 2.36 liters. I'm going to come back to that one. 2.36 liters of solution. That's what we have. The concentration, though, is in mass percent. So this needs to be converted to how much mass is that? That's where the density comes in. So if this is that many liters of solution, in order to use the conversion to mass of solution, we need to convert this to milliliters. There. So that's milliliters of solution. Now, we can convert milliliters of solution to mass of solution with our density, 1.42 grams. That cancels. Now we've got grams of solution. Okay. Now that we've got grams of solution, we can find out how many grams of HNO3. Okay. Because we know that the ratio is 70%. So for every 100 grams of solution, we have 70 grams of HNO3. So let's stop there. That gives us grams of HNO3. We'll do that calculation, split it out. 2.36 liters times 1,000 is 2,360 milliliters. That's reasonable. Then times 1.42 gives us mass of solution. And then times 70 divided by 100 gives us 2.346 times 10 to the third grams of HNO3. Now let's see, is that reasonable? Yeah, 2,000 grams. Got 2,000 liters. Yeah, okay. I'll buy that. That's the grams of HNO3. Now we need to convert it to moles. So we just need conversion factor to go from grams to moles. HNO3. Right, hydrogen 1.01. Nitrogen 14.01. And oxygen. 3 times 16 is 48. 63.02. Divided into that value. And I get 37.2. Let's see, where am I? Oh, here we go. Rounding error. This is 37.8. Let me check my math. 2.36. Yep. There. 1.42. Yep. 70. Let's do that again. I could have made a mistake here. Two, three, four, six. How about this? Did we calculate that one right? 6302. Add it into that one. 37.2. That was right. Okay, so when all else fails, you would be within your rights to say none of these. If that's but if you put A, then you probably still get it right. So if one like this shows up on the test, watch it close. Actually, any of them. If you have none of these as your example, and the answer is not exactly the one that's proposed that matches your calculations, then when you put none of these, then all you have to do is show me your work and you got the credit. All right. Let's see. 38. You have two solutions of sodium chloride. One is 2 molar, the other is 5 molar. Okay, two solutions. So solution 1, let's call it A. Solution B of sodium chloride. Okay. One is 2 molar solution, and the other is 5 molar. Okay. You have much more of 5 molar. You have much more volume. So volume of B is much greater than volume of A. Okay. You add the solutions together. Whatever volume you have, put them together. What's your concentration? Which of the following could be the concentration of the final solution? Okay. Now, if I tell you, if I propose, what would the concentration be if these two were equal? It'd be halfway in between, right? So it'd be 3.5. But it's not that because this one's greater. So it's got to be greater than 3.5, definitely. So the concentration of the mixture, A plus B, must be greater than 3.5. We know for sure. All right, the other thing that you want to look at is, are any of these selections less than 2 or greater than 5? Well, actually, if they're less than 3.5, they're out. But if they're greater than 5, they're out too, because you can't dilute a solution and get more. Right? Okay, so that's where I would start. 7.2 can't happen. 7 can't happen. So it's either B, C, or D. 4.8 is greater than 3.5. Okay. 2.9 is less. 3.5 is equal. It's got to be D. That's the only possibility. Ready to tackle number 50.
Should have shut it back. I didn't think about
That's all right.
it.
It won't shut on its own because there's positive pressure in the room. No, negative pressure in the room. It'll keep opening the door. What's the normality of 1 liter of sodium hydroxide solution that contains 18.2 grams of sodium hydroxide? So we got 18.2 grams of sodium hydroxide. In 1 liter. So the volume is 1 liter. So really all we need to know is moles. And moles of sodium hydroxide would be the same thing as equivalence, right? Because normality is number of equivalents per liter. So 18.2 grams of sodium hydroxide is how many moles of sodium hydroxide? Sodium is 23.0.
Yeah.
Oxygen is 16. Hydrogen is 1.01. So that's 40.01. Grams, moles, 40.01. So divide that into 18.2. I get 0.4589. 589 moles of sodium hydroxide, which, for argument's sake, since there's one hydroxyl for every mole, this is also 0.4589 equivalents. Because there's only one hydroxyl. So then we can say 0.4589 equivalents per 1 liter, and obviously 0.3 significant figures. 4, 5, 9, normal. Did it again. Yeah. None of these. Okay. So there you go. Same argument as before. I'll check the exam closely before I give it to you because you shouldn't have to make that choice. If it's none of these, it would be way, way, way far away from the correct answer. Wouldn't be that close. Okay, 52. Wait a minute, there's another one. I'm looking at the setup. Oh. Okay, I didn't check that closely. They're similar scenarios as ones that I wanted to cascade through, but they're slightly different, each one. Yeah. So that blows my ship out of the water. I think what I'll do is take one of them and work it through to answer the question with a single set of data so that we don't have to recalculate every time. That'll become obvious when I get there. So we'll come back to them. Let's do 55. Let's see. In the following acid-base neutralization, 1.61 grams of the solid HC6H5O neutralized 11.61 milliliters of aqueous sodium hydroxide. By the reaction, sodium hydroxide plus this one yields water and the salt. Okay. So what do we notice? We notice that there's one hydroxyl per molecule and one acid hydrogen per molecule. Remember the difference between these hydrogens. If it's an acid, the hydrogen that can dissociate from the molecule is first. And any other hydrogens come later, they're fixed. They cannot move. So the only hydrogen of importance here for our acid-base reaction is that one. Okay, that means they're 1-to-1 acid-base. Okay. So in that case, all we have to do is say 1.61 grams of this compound, HC6H5O, right? Yep. Oh, I know what that is. That's phenol. You ever sprayed your throat, sore throat with, let's see, what's it called?
Septic.
Yeah. Is that what it's called? Chloroseptic? It's green. What's the green one? There's a green one. It has phenol in it. And what the phenol does is it calms the nerves. It deadens the nerves.
Always have the cherry flavor.
Yeah. Okay, so we have 1.61 grams of this, 1.61 grams. What we need to know is how many moles does that represent? Because, well, let's go back to the basics. Right? Molarity of the base times the volume of the base equals molarity of the acid times the volume of the acid. Right, what do we know? 11.61 milliliters of this. And its molarity is what's the molarity? Wait a minute. We're not given the molarity of the, we want to know the molarity of the base. Right. This is, that's the wrong side. 11.61 milliliters of the base. And this is our unknown right here. So, molarity times volume is moles. Right? Molarity times volume of the acid would also be moles, but we don't have it in solution. It's a solid. So we can substitute for this moles of acid. Moles of acid will be neutralized by moles of base. You see what I just did? I just put in the equivalent for this one, right? Molarity equals moles per volume. So moles equals molarity times volume. But we don't have molarity and volume for the acid. We just have the ability to find out how many moles it is. So we can substitute moles of acid here for moles of base here. So the moles of acid is what? 1.61 grams. And all we need is a molar mass for that compound. Right? So we have 6 carbons.
If I'm right, I got 94.7.
Okay. Yep. That's what I get. 94.12 divided into 1.61. (1.71 times 10 to the minus 2. 1.71 times 10 to the minus 2 is equal to molarity of the base times the volume of the base. Okay. In this case, we've got moles here. And we have to adhere to the strictures here. Moles, this has to be liters. So we got to convert this to liters, which is what? 0.01161 liters. Okay. So now to find this, we just divide that by this. 0.01161. Okay. And I get 1.47. 1.47 molar for the base. There it is. Okay. Did I lose anybody in this logic? Okay. Good deal. That's 55. Let's see. 59. what volume of 0.176 molar sodium sulfate, 0.176 molar sodium sulfate solution contains 1.01 grams of sodium ions. The mass is going to be 1.01 grams of sodium ions. And the question is, what volume? Okay. So if we look at volume in relation to molarity, we know that molarity equals moles divided by volume. So volume is going to be moles divided by molarity. This is going to be moles of sodium ions divided by molarity of sodium. So can we find moles of sodium ions? We have to understand, in order to do this calculation, that a sodium ion is virtually the same as the sodium atom, because the electron is 1/1800th of the mass of a proton. Right? So the loss of that one electron has virtually no impact on its molar mass. So we can take the molar mass of sodium and find out how many moles of sodium ions we have. Just need 1.01 grams of sodium ions. Be how many moles of sodium ions? This thing's starting to get weak. So sodium is 23. Yeah, 23. That would give us the number of moles of sodium ions. 1.01.3 is 4.39 times 10 to the minus 2. 4.39 times 10 to the minus 2 moles of sodium ions. Okay. Now, what's the molarity of sodium ions? Right, we've got this part right here, right there. We need molarity of sodium. Well, we have molarity of sodium sulfate. Right? So if we say 1.176 molar sodium sulfide, excuse me, I said sulfate, sodium sulfide. Then what's the ratio of sodium sulfide to sodium? Well, for every one of these, you get 2 of those, right? So it's actually twice that. 0.352 molar sodium. Now we got this one. We just have to say moles of sodium ions, 4.39 times. And it's kind of squiggly. 10 to the minus 2 moles divided by 0.352 molar. And then that will be 0.125. 0.125 molar sodium ions. And there it is. Oh, excuse me. Volume. I'm not paying attention to my units. This is moles per liter. So moles cancel, liters goes up. There we go. 59. Oh, running out of time. Let's see, can I get to the 62? I think that's one of them. No, it's different. Let's leave 62 also. And got time to work one more before I get to the that series.
So Nate did that one before my report.
Huh?
I have to work tonight.
Oh.
Yeah,
What time?
so.
Oh, I need some sleep. Okay. Just checking this. Waste of time. Okay. Let's go. We'll come back to 74 if we have time. But I do want to go to it won't Titanic. Can't hold it down and have to do individual pages. Should that do? Probably give that manual circle. 26. Let's look at 26. Here we go. Let's see, how far can I go? I can move on a little bit. Not quite that far. Yeah. Okay. We got a reaction here between silver nitrate and sodium chloride. And the question is, what's the concentration of silver ions in solution after the reaction is complete? All right, so the reaction between silver nitrate, right? 1 plus, 1 minus, and sodium chloride produces what? The double replacement reaction. Sodium substitutes for silver. So sodium nitrate, sodium nitrate is soluble. That's what that solubility chart is for. Right here, this one. That tells you that sodium nitrate is soluble, and then silver and chlorine together, or chloride, silver chloride is a solid. So that's your reaction. It looks like it's already balanced. Yeah, it's already balanced like that. Okay, now we can put in, what do we know? 200 milliliters, 0.1 molar, 200 milliliters of 0.1 molar silver nitrate. 95 milliliters of 0.1 molar. I'm leaving out some zeros back in. Sodium chloride. The question is, what's the concentration of silver ions? You've got silver ions on this side, but when the reaction occurs, some of them are going to be over here in the solid. They're not ions anymore. At least they're not in solution. Okay. So we've got a reaction where we have absolute amounts of both reactants, which means one of them is going to be limiting. So how do we tell that? We find out how many moles of this here, how many moles of that there. So this would be, I'm going to use millimoles, milliliters times molarity. So this is 20 millimoles of silver nitrate. And this is 9.50 millimoles of sodium chloride. So if all of this is used up, I think we can tell right off. 20 millimoles, since they're 1 to 1 to 1 to 1, this would produce 20 millimoles of that if all of it were used. This would only produce 9.5 millimoles. So this one is the limiting. So that tells us that we are definitely going to have some silver ions left over, because there are only enough of them to neutralize, to combine with this chloride to make that. And you're going to have some left over. So this is millimoles of that compound. It's also millimoles of chloride. This is millimoles of that compound. It's also millimoles of silver ions. Okay? So since they're 1 to 1, 1 silver, 1 chloride, we're only going to use up 9.5 millimoles of this. Okay, 0. Do better than that. And 9 from 19 is 10. So we're going to have 10.5 millimoles of silver ions still in solution. Okay? Now, how do we calculate, what's the question? The concentration of silver ions in solution after the reaction is complete is, oh, it just says greater than or less than or equal to 0.1 molar. All right. So how do we calculate molarity here? Millimoles divided by milliliters is molarity. Can we prove it to you? Okay. If we do millimoles divided by milliliters, take the milli out. Say milli times liters and no moles. Moles times liters. Milli cancels. Moles per liter. Okay. So that equals molarity. So if we have this many millimoles of silver, then we need milliliters of solution. Well, we still have 295 milliliters. So 10.5 divided by 295 milliliters is 0.036. 0.036 molarity. Silver ions in solution. Okay, now that we have the value, we can look at the answers. Silver ions do not participate in the chemical. Well, that's false. Less than 0.1 molar. Yes, less than 0.1 molar Are there any others? This one's also less. It's not greater than. And it's not zero. Because this was not completely consumed. It's excess. So it's either B or D, less than 0.1. Okay, let's see what else is given. Some, but not all, of the silver ions are used to make the precipitate. That's true. Even though silver ions do not react, we stop there. It has to be B. Not all of the silver ions react to make up the precipitate. You have some left over in solution. Okay? Let's see. We'll leave that there for a second. What else can we say? We could calculate the concentration of sodium in solution. Okay. All we need is millimoles of sodium, which is equal to millimoles of chloride, because they're 1 to 1. Divide by this volume, that'll give you the concentration of sodium in solution. Nitrate. Nitrate doesn't enter into that compound. So we have this many millimoles of nitrate in the beginning and the end, divided by the volume. We can calculate the concentration of nitrate also. What else? Chloride. All right, we're going to use up all of the chloride, right? It's limiting. So how much chloride is left in solution? 0. As near 0 as we care to calculate right now. For this class, if you were in general chemistry, we'd have to say how much chloride is in solution. And that's an equilibrium problem that we have attacked. Okay. We got 7 minutes. I don't know if we have time to do that last one. That's not it. That's not it. There it is, 62. Scroll some. It's easier to do it this way. Sodium phosphate reacts with lead nitrate. What's the concentration of phosphate ions left in solution? This is similar. I mean, it's a double replacement reaction. Lead 2 phosphate is insoluble. Right? You would have a reaction. Eesh. You would have a reaction between sodium phosphate. So this is a word problem that means you've got to write the compound correctly. That's in solution. And then lead 2 nitrate is also in solution. And then it yields lead 2 phosphate, which means 2 here and 3 there. That's a solid. And then you're going to have sodium nitrate left over. So this one, aqueous solution. These are both aqueous. So this one you would have to balance. Let's see. Let's start with lead. 3 leads. That means 6 nitrates. 2 here, 2 phosphates. 2 phosphates, 3 leads. Okay, balance. 2, 3, 1, and 6. Then what are you given? 15 milliliters of 0.3 molar. 0.3 molar. And 20 milliliters of 0.2 molar. So what you would have to do is find out what's the limiting one and say, how much solid can be produced? Right. If this is limiting, if limiting, then 0 molar phosphate. But if this is limiting, you will have some excess here. And then that means you'll have some phosphate left over. You have to find out how much phosphate was used to make that product, and then subtract it from what you started with. Then divide it by the combination of the volumes. Okay. I see that 64 down there. We didn't look at that. It's a definition. When a solvent, yeah, I got 3 minutes. When a solvent has dissolved all the solute that it can at a particular temperature, it's said to be, say what? Saturated. Yep. If it holds all it can hold, it's saturated. What if it's got more in it? Right. If it's got more in it than you would expect at that temperature, it's supersaturated. What else is characteristic of those solutions? They're very unstable. All you need is just to look at it cross-eyed and it'll precipitate. If it has less, it's unsaturated, right? What if it's close, but not saturated? It's close to saturated, but not all the way. That's a concentrated solution. If it has just a little bit of solute in there, it's dilute. Okay. Terminology. That's it. Unless you have any questions.